Really appreciate everyone coming out for this panel discussion on Wi-Fi and LTE comparison. I think, this is a Wi-Fi focused conference, and we're really excited to be here for our first public demonstration of our private LTE solution in CBRS. So thank you all. And this is really a kickoff of the discussion for us on CBRS and private LTE. So the panel discussion is going to really kickstart a community effort for us. So in the coming weeks, we're going to be announcing a community initiative that will be posting information on CBRS and private LTE in blog, video, podcast formats, as well as an online discussion forum for people to chat about the new technology, what its implications are, to learn, and to grow as a community as we deploy these networks for our enterprise customers. So be on the lookout for an announcement in the next couple of weeks about that community initiative. So with that, I'll kick off our panel discussion here on Wi-Fi and LTE. The goal here is to understand each technology's strengths and weaknesses from a technical as well as an operational aspect, and what implications that derives for different use cases in the enterprise and where each technology has strengths and can be best positioned. So it's very complementary in nature. We're not trying to pit Wi-Fi against LTE or anything like that, but just understanding their technology and what their differences are. So with that, we have compiled and graciously a group of panelists have come to participate in the discussion with us. Very quickly, where is the microphone? Up here. Have you turn it on, and I'll have you do brief introductions of yourselves, maybe 10 or 15 seconds on who you are, what your background is, and what your experience is.
My name is Sam Clements. I'm an engineering director out of the Office of the CTO for Mobility at Presidio. We're a nationwide VAR here in the States. CWNE, CCIE Wireless, and I've done mobility now for 20 some odd years in the Wi-Fi space. I apologize.
My name is Manon Lessard. I work for a large university in Quebec City, Canada. I'm their wireless specialist. And my experience with mobility is mainly wireless. I've been doing this for 17 some years.
Hi, I'm Mehmet Yavuz. I'm coming from the cellular world. Long time at Qualcomm. Worked on 3G, 4G, 5G quite a bit, and now I'm with Celona as CTO and co-founder.
Hi, Jonathan Davis, or JD. I work for municipal government right now, but come from a history of manufacturing, warehousing, and complex Wi-Fi environments like that, CWNE, and 12, 13 years in wireless.
My name is Jennifer Huber. Wow, that's really loud. Jennifer Huber. I work for Worldwide Technology. I'm a mobility solutions architect. I'm also CWNE. I got my start working in Wi-Fi back in 2002. I'll let y'all do the math. I'm glad to be here.
Hi, this is Jamal Ramoud. I'm a sales engineer at iBwave. I have like 15 years of experience in the wireless industry, but mainly in the cellular. So I've done many LTE projects, and now I'm kind of learning the Wi-Fi. Started with CWNA, CWDP, and just finished CWAP with Peter.
Excellent. So I'll just have you guys hand on to the mic and pass around as we answer questions. So with that, we'll dive into some technical and comparison aspects between Wi-Fi and LTE, and we'd just like to get the panelists' perspectives on those and what their insights are into the technology. So let's start with just the basics of spectrum, right? So on the Wi-Fi side, we have unlicensed spectrum, over 600 megahertz totally available across the different bands. Channel widths varying from 20 to 160 megahertz. And radar detection with a protocol called dynamic frequency selection. On the LTE side, we have shared spectrum, 150 megahertz in the CBRS band. Carriers are 10 or 20 megahertz size with carrier aggregation, up to 5 carriers. And the radar detection is with environmental sensing capability, which is centralized. So the idea, just to start the first one off, is that what are the implications of the different underlying aspects, for instance, on this one with spectrum, and how does that lead to different capabilities between the two technologies and where they might be better suited for use cases? So does anybody want to kick it off?
Well, I will start. I will say that the biggest difference is the amount of bandwidth that's available in Wi-Fi versus LTE, but that's not necessarily a bad thing, because there could be specific, very specific use cases where you don't need a whole lot of bandwidth, but you need the signal spread. And I can see where LTE would have a play in situations like that.
Maybe one of the things that really jumps out to me, and you know, when I think through this, for those who might not have heard Chuck Lukashevsky's talk maybe 3 or 4 years ago, when we cut the channel width in half, we actually gained 3 dB additional SNR, right? So our noise floor drops an additional 3 dB. And while 10 meg carriers are certainly one of the choices, we can actually go lower than that in CBRS. And so going into that super, super low, where we think of as, you know, neg 90 as being, you know, unheard of, below usable signal, you're still in prime signal space in CBRS. And I think that's going to be one of those things that really gets heavily used, and it's going to take for especially Wi-Fi people coming into CBRS, that's going to take a rethink for us, because it means more space, right? A single AP, we'll call it for this, is going to provide us much greater coverage. But also at that edge, that cell edge, there's much more capability that we have there that in Wi-Fi we just simply don't have. So you're right. You're not going to have the incredible bandwidth that we have right now, right? Transfer capabilities. But for so many applications where you need smaller amounts of data throughput, this is going to be really key.
Okay, so this is, yeah, all great points. And maybe one thing I'll add is 150 megahertz of cellular spectrum is a lot of spectrum. None of the operators in US has this amount of spectrum today. So LTE and also 5G is designed to work very efficiently with the spectrum. So that's something to keep in mind. So if you give this much spectrum to an enterprise, which is more than what Verizon or AT&T has, there's a lot of potential in that spectrum. And also in terms of the use cases and the kinds of spectrum differences, I think is important, because the unlicensed spectrum is unlicensed spectrum, and you have a lot of it, and it's great for many use cases. But whenever you want some predictability and reliability, then there's a difference between the two spectrums. So it's really almost like apples versus oranges, you know? If you have 150 megahertz of interference-free, clean spectrum, there are many applications you can run on it and get the reliability and predictable performance. Yep, sorry.
Yeah, no,
I can keep talking about it, so please go ahead.
It's just that I didn't want to lose my train of thought. You were bringing many good points, and I was thinking of, and all through the deep dive, I kept thinking of something that's been a real big pain for us. We have a really woody campus, and we have underground tunnels, and I was thinking of all the applications of the possible LTE, and voice has always been a pain for us on Wi-Fi, and I'm thinking that within the confines of Wi-Fi, we're still struggling, but with LTE and what you're offering, in the semi-licensed scheme, I think it's going to help us a lot.
Yeah,
and you're finally segregating voice from all the
other
crap.
Yeah, I mean, I think enterprises deal with contention. That's probably the number one problem, whether it's my neighbors or whether it's internal applications and use cases, that they're always struggling with where do I put my stuff so it doesn't fight with somebody else. And it's the problem of, okay, you've got a whole bunch of channels, but you've got to share them, or do you get these really narrow channels that you can lay claim to? Using the sandbox analogy, I'd much rather have a room at home with a couple of arcade games in it that I know is mine, that I can play, just go and do whatever I want, versus having to go off into the sandbox or the playground where, there's 100 kids running around, right? You have a high degree of predictability, and if you can claim that high degree of predictability, you can do so much more with the spectrum from a business use case perspective.
Yeah. Jamil, do you want some? Here.
Just want to add something regarding the bandwidth. Yes, when you see maximum 20 megahertz for LTE, you feel like it's not enough if you want high throughput. But remember, there's carrier aggregation. And what does this mean is that you could combine 5 20 megahertz channel and you get a throughput of 100 megahertz channel. So, and then with 5G, you could do more actually. So, and like Mehmet said, 150 megahertz in cellular, that's a lot of spectrum, and it's a clean spectrum. Efficiency is high, so for now we're going to see like very, very good performance, I believe.
Any other last points anybody wants to make before we move on to the next?
I can make a little bit.
Okay.
Maybe a little bit nerdy comment in terms of the operation of the CCA versus the universal frequency reuse, right? One way to think about this is in Wi-Fi, typically each AP ends up being on a different channel, and you end up really, you can start with maybe in the 5 gigahertz, you have what? In Uni 1 and Uni 3, total of 180 megahertz spectrum, but you start splitting it across APs, and you end up maybe using 40 megahertz channels, and if it's a very dense deployment, you end up going down to 20 megahertz channels per AP. Versus in the cellular case, in the CBRS case, all of the APs can operate on the same channel, universal reuse, without partitioning the spectrum amongst them. So that's one thing to keep in mind.
Great. Okay, maybe on to the next topic. So let's talk a little bit about radio characteristics. So output power differences between the two technologies. We talked a little bit about receive sensitivity already. Maybe we talk about how that translates into coverage. SNR versus SINR. There's some differences there between the two technologies and actually how those operate. And maybe chipsets and how they're implemented as far as defined performance characteristics and thresholds based on, let's say, data rate shifting and performance targets. So who wants to lead off this one?
I will. So 2 weeks ago, I was working with a group of experts for CWNP, trying to overhaul CWNA and define a new CWCP. And Jamel, we had the discussion about SNR and SINR, and Jamel had an awesome explanation about SINR. And I'm sorry, but I would really appreciate if you could give it to us, because I think that in the wireless world, in the Wi-Fi world, we're not really getting the real meaning of SINR.
Okay, yeah, good point. Basically, if you go to the basic math, SNR is just your signal versus your noise. And your noise is pretty much wideband. You can't do anything about it. It's just noise. When you go to SINR, you're calculating your noise plus interference. So you may argue, yeah, interference is noise. No, it's not noise, because it's like saying energy detection is noise and then carrier sense is noise. No, it's not the case. So interference is something you can do, you could mitigate, you could do something about it. You could reduce power, you could change channel, you could remove it completely. That's the interference. And the big difference is that the SINR could be different from a resource block to another. Why? Because somebody might be using a resource block on the same channel from another server or another eNode B. So you use another resource block with less interference. And it's not like channel wide, it's by resource block basically. And one more thing is that when you combine all the interference, so the more interference you get, like the more interferer, the more other people transmitting in the same channel, your interference will increase by composite power. So if you have two other interferer, the signal level of this interferer will be actually 3 dB higher. Then another one is 4.7, then another one is 6 dB higher. So the more interference source, the more your interference will get higher. So this make it really different in terms of calculation versus just the SNR, which is your noise floor. The noise floor could get high or low. It's going to stay your noise floor. You can't do anything about it. That's the point. I hope I explained it the same way as last time. Okay. Anybody else?
I think the number one problem I see when we look at numbers like this is especially from Wi-Fi professionals, we have been grappling with this mentality of designing for coverage versus capacity over the past decade and a half, right? Where we were designing for how big of a cell can I get, and we've had to shift in the Wi-Fi space to say, no, we're designing for density, smaller cells and the like. And you ratchet back 15 years ago when we were looking at cell sizes that were in the 20 to 30,000 square foot range in a warehouse with APs cranked to max power with high gain antennas. And we've been beating the Wi-Fi crowd over the head for the past decade going, no, don't do that. I think that this requires some rethinking from the Wi-Fi professional's perspective, which is the reason that was bad in the Wi-Fi space is largely because of protocol inefficiencies. Those protocol inefficiencies don't exist in the they're not the same inefficiencies in the 3G, 4G LTE space. And so those really, really large cell sizes that we've just been so averse to deploying for many, many, many years requires a huge rethinking, I think, especially as you're trying to drag Wi-Fi professionals into the conversation. Should say it all again, right?
We just changed the noise.
Yeah, maybe just to add to that SINR versus SNR discussion, one way maybe to think about is also in the Wi-Fi case, when either AP or the station or device transmits, everything else is silenced, right? That device grabs the medium and transmits, and the only thing it's fighting against is the noise floor, like the thermal noise floor at the receiver. In the cellular case, simultaneously multiple APs or simultaneously multiple devices are transmitting. So their signal is now competing with the interference from all other devices plus the thermal noise. So it is the I is the interference, N is the thermal noise component. Now, what happens is in the cellular you end up operating at maybe lower values of the SINR, but you have more spectrum, more opportunities, and if you do the math, I mean, this goes to the Shannon's theorem and how that log curve occurs, you end up showing that as a network, you get better capacity that way. Because you're not unnecessarily silencing everyone. Every time transmitting is getting some part of the capacity, and also you get some predictability. So it's not like you don't know when you'll get an opportunity to transmit next. Right, in the Wi-Fi, when you get the opportunity, you can get very high throughput, but if the medium is congested, now everyone is trying to grab the medium, and you don't know when will be the next opportunity for you to get the medium. So that's another way to explain, I guess, the difference between the two.
Anybody else want to make any points on this one? Okay, on to the next one. Let's talk about some protocol characteristics. So, yeah. So distributed contention in Wi-Fi, centrally coordinated transmissions in LTE. Hidden node issues can be prevalent in Wi-Fi depending on the environment and whether or not RTS, CTS is used versus LTE where it's scheduled, so it kind of prevents those hidden node issues. Some OFDMA, getting really technical on the PHY layer. OFDMA is frame-based in Wi-Fi, so you're scheduling multiple users in the frequency domain only versus OFDMA and LTE, you're scheduling in both the frequency and time domains. So there's a little bit more user packing that can happen in there. And then clients are assigned an RU for the entire frame duration in Wi-Fi, so since it doesn't have that time domain element, you might have to pad some of those subcarriers or those resource units if all the client transmissions don't require the same amount of time versus assigning tones to OFDMA and LTE to clients, and you can pack those clients in there a little bit tighter with less padding. So who wants to kick off this one?
One of the things that keeps coming up here is the spectral efficiency. And when we think about Wi-Fi, we know that you take whatever your Wi-Fi speed is, right? We know right away for AC, you take 40% away for management frames. But that 40% doesn't take into account your retransmissions because you have, hidden node issues or any of those other problems. When you start considering that with what we're saying with LTE is that goes away, the majority of that goes away because of the way the spectrum, number one, is divided, not just spectrum, but time-based, right? So we're no longer talking over each other. We don't have to worry about a lot of those collisions and things that may take place in Wi-Fi. What we also start seeing is those problems that we have with, for example, roaming, right? That goes away too because of that. A lot of those knock-on problems that we have in Wi-Fi that translate into other problems, those also go away. And so when we're thinking about this, what we have to begin asking ourselves for is what we've previously designed for, right? Worked very hard to design for unique problems to Wi-Fi. Well, as those get taken away, what does our design look for? And it goes back to the previous slide with that space, the amount of space that we can cover for, and your comment, Sam. And you start asking the question, well, with the capabilities and with this efficiency that we have, not just for airtime, but also efficiency for roaming and all of the other characteristics of getting on the network, right? Because we don't have an authentication. There is no four-way handshake. All of those things go away, right? Then you start asking yourself, well, again, roaming, or I'm just completely blanked on all of the other, I guess, various, things that we have to constantly talk about and think about in Wi-Fi that in this environment doesn't exist. So again, we're not saying that LTE is going to replace Wi-Fi. Let's be very clear on that. But in use cases where there are going to be plenty of use cases where we are going to make the decision, should I put this on LTE or should I put this on Wi-Fi? And when we start looking at applications or we start looking at use cases in that regard, and we start looking at these features and these characteristics, that really starts to change the conversation.
And even though it's not exactly on the slide, one of the things that you said that was so markedly different was about the different, the end-to-end QoS, the dynamic QoS, that where a device can have different IP addresses and VLANs assigned to different traffic and have different rules placed upon it, just out of the like as inherent to the way that the thing works. And so I started to think about the use cases like where this could replace like maybe an indoor DAS solution or maybe an emergency signaling system on a college campus because it's got a really wide spread and it's low bandwidth and low band, and all the different things where use cases where you need that end-to-end QoS, you need the reliability, the schedulability, all of that stuff that comes with the solution, where there's a lot of use cases for it. Yeah.
Yeah. Just want to mention something about the scheduler, because in LTE, the fact that you could schedule the transmission and you could deal with different client or end user device. I've seen it in action in live games like at sport events, and you see live stats and you see like the connected users going higher and higher and higher, and you see the throughput going lower. So what it's doing is actually getting more people connected, but just giving them less throughput. So in terms of capacity, it's handling very well. And then at a certain point, if you get too many users and they cannot go to another cell, then it's just the scheduler cannot do it anymore. But as I've seen it in action. I don't think any AP with 20 meg channel like equivalent could handle as much user. I've seen like 700 users connected simultaneously. It's, well, throughput is nothing, but at least they are connected. And that's the beauty of LTE, I would say.
Yeah, I think very good comment on the scheduler, because with this predictable, reliable kind of QoS, you can also keep supporting more and more users. For example, in terms of voice capacity, you can go to few hundred of simultaneous VoLTE users, voice over IP users in LTE. And I think another important point is about the OFDMA. So I think it's really great that Wi-Fi 6 is moving into OFDMA. And I've been on that journey. We started in like 2009 when we were first writing the first scheduler. And I mean, there's a lot of enhancements along the way. It takes quite a few years to get to a level where you can really start offering quality of service. I think it will take some time, the Wi-Fi ecosystem, to get there. And another aspect is, in the current implementation, the AP still needs to grab the medium and then schedule the users. But until the next opportunity to grab the medium, there's no guarantee of service for all the users that the AP is serving. So I think that will be another enhancement down the road, potentially in terms of maybe coordinating the APs to work together simultaneously to kind of break that wall. Because currently there's still a roadblock in my mind for the Wi-Fi operation.
Okay. Any additional points or? Okay. Next one, we've talked a little bit about it already, but frequency reuse and quality of service. So some of this we can either touch on additional points or move on if we've already covered it. We talked about frequency reuse in Wi-Fi requiring that spatial separation because of preamble detection and deferral. Whereas in LTE, we talked a little about IC-IC, which is inter-cell interference coordination, scheduling those transmissions within the same frequency channel across multiple APs or eNode Bs. Again, Mehmet just brought up on Wi-Fi how the AP must contend to acquire a transmission opportunity before it can actually schedule OFDMA transmissions for clients. Whereas in LTE, it assumes control of the channel and it's completely scheduled without having to do any contention. And then on the QoS side, there's some differences on statistical prioritization in Wi-Fi, where it's more of an aggregate. In aggregate, we're going to give general priority to classes of traffic, but nothing is guaranteed within that class even. Yeah. So you might notice this, with large amounts of voice, high density of voice clients. Whereas in LTE, we can have each individual client set up EPS bearers and schedule their transmissions individually, more so than as a group. So who wants to kick this one off? Did we cover it? Do we want to cover anything else?
Just to add about the SINAR topic, actually the inter-cell interference coordination plays a lot into handling what is a good, let's say, resource block to transmit on it or not. So it's managing between the other cells or between the other eNode Bs what chunk of spectrum to use. And it's kind of coordinating the effort of reducing the interference. And this is included in the SINAR calculation. So even if you have a lot of transmitters, the fact that they are coordinating, then it's kind of helping transmitting all together and dividing the spectrum whatever is needed, and then if not, then they're just going to transmit and get lower throughput. That's it.
Okay.
You mentioned these points, but as I understand personal experience, right, as I moved from Qualcomm to Ruckus and understanding the Wi-Fi details more, one thing that really occurred to me is when the system is not really loaded, you can really get to very high data rates with Wi-Fi, but then when you look at the other extreme of the venues or dense deployment environments, what you really end up doing is a lot of frequency planning, right? And then you can have maybe 8 different channels, and then each AP, when you really need the capacity, you end up using a small bandwidth per AP. And that's when it starts hurting you in terms of the operation of Wi-Fi, in terms of that requirement of during the channel, grabbing the channel, or listen before talk, or CCA type operation. So that's kind of the two extremes in my mind. And it is not loaded, you can get really great peak rates, but as the system gets denser and loaded, it becomes harder and harder.
Okay. On to the next. Oh, you want to comment?
I was going to say, this absolutely is one of the biggest problems I had when I started learning about license frequency use, is that we in the Wi-Fi space have dealt with contention-based medium for our lives. And the first time somebody said, no, you can have multiple radios in a room, you can have 10 of them in a room if you want, I about fell over. I'm like, how do you do that? Because it's been beating our head. Yeah, it feels wrong. Yeah, and so these design principles that we have as Wi-Fi professionals, we're at WLPC, right, wireless networking, practically none of those mean anything, largely in part because of frequency reuse capabilities and scheduler and protocol and negotiation, all that fun stuff. So it's one of those things that as Wi-Fi professionals, we need to unlearn those behaviors if we're going to survive in this conversation where we have to be dealing with CBRS.
Yeah. Okay, on to the next one. Let's talk a little bit about mobility and roaming. So in Wi-Fi, roaming is controlled by the client. In LTE, the handover is controlled and coordinated by the infrastructure. In Wi-Fi, we have roaming coordination defined, but not necessarily well supported with some of these amendments like 802.11k, R, and V, and the handover coordination that's very well standardized in LTE, that communication between infrastructure and clients. Roaming oftentimes in Wi-Fi is dependent on the client's implementation and their algorithms, what the quality of those drivers are. Whereas in LTE, mobility management is based on standardized metrics and thresholds that I have a couple up there, like receive power, SINAR, RSRQ. And then just speed of handover. LTE can achieve very high speed handover, and much more so than Wi-Fi. So some of these topics on mobility and roaming, let's dig into. Who wants to lead that one off?
I'm tempted to add to the handover controlled by infrastructure. Finally. Finally, we get some say in the decision. That's not just vain hopes and a trial and error. And the high-speed mobility handover is super interesting because, I mean, I don't know about you guys, but on my campus, I have a lot of security personnel. They're running around with phones that cost us a fortune, and with eSIMs and this system, I see it where we could do something.
I just want to test 700 kilometers per hour mobility handoff.
Fun one on that one. Jamel sent me a video. It's a fighter jet that they tested.
Nice.
If you look on it.
So, yeah, it is. Okay, so everyone awake now? Yeah, they're on the left side in Wi-Fi, that 802.11 KRV, or RKV as we call it. What we all know is those protocols have been around for a while, and we can probably count on one hand the number of devices that actually have those well implemented, maybe even one finger. Maybe, right? The reality is that in Wi-Fi, and I won't bash the Wi-Fi Alliance right now, but I hate that. No. The reality is that our standards bodies leave a whole lot to be up to the manufacturer, and the manufacturer, in many cases, make business decisions, not technical decisions, right? So what we end up in, especially in these areas where we're talking about mobility and roaming, we end up with devices that either don't support those standards or support those standards in half-baked fashion that might actually get worse as the driver, is incremented upon. And But when we look at LTE, the devices that we're going to be testing against, right, the devices that are going to go into this are the same devices that manufacturers want to sell to Verizon and AT&T and carrier du jour. And those carriers have something that we don't have, and that's they have the ability to say no. They have the ability to say, you're not putting that on my network. And so it absolutely has to function the way the standard says it has to function. There's none of these 16 different optional things that may or may not work based on, you know, which combination you happen to have. That's the reason you have that high-speed handover, right? Well, one of the reasons. It's also that make before break mentality. There's a lot that's built here because it had to be built here, and it was never built that way for Wi-Fi. So you mentioned the security personnel driving around, you know, on golf carts or whatever at campus. I think about, you know, 1.2 million square foot warehouse. It's got people in forklifts or tow motors, whatever you want to call them, that, you know, go by as you're walking with your, you know, doing your survey. They go by fast enough that you're going, I'm just glad I didn't get hit by that, right? They're moving and they're coming around corners and hopping between access points so fast that, in one situation I was in 6 or 7 years ago, we actually had to have them reduce the speed of the forklifts because there was simply no way we could run fast enough at that speed. And by dropping their speed of their forklifts down 2 miles an hour, suddenly all the clients were able to stay on and run, right? Which, when you think about, I mean, you know, it's the tail wagging the dog, right? I mean, that's where we're at now. So there are a lot of situations where whether or not the Wi-Fi Alliance is doing its job or not, our clients certainly don't hold up their end of the bargain. And that's a problem that we no longer face in a CBRS world.
Regarding the speed, you could check on YouTube. There's a video from Ericsson. They tested with a jet fighter, and it actually was working on 700 kilometers per hour. We could tweet it maybe later or something. Regarding the mobility, yeah, it's really cool to have something where you could control how the client or the UE behave in terms of where to change server. So you could control it by RSRP, which is signal level, by SINAR, or by RSRQ. It's like saying, if my channel is loaded or the quality degrade, please move to another cell. That's cool, but we said a lot of good thing about LTE, but it's also not cool for one use case, if you're not moving. So when you're moving, the handover is great. You're moving from one position, you go to another position, you switch cell, it's magical, there is no problem. If you're in a situation where the thresholds are met and you're not moving, and you have to switch to another server, but this server also has the same thresholds, what we call a handover zone. Let's say we have this cell here, and then we have another one in the corner there, and we are in between, and they are on the same channel. So then you are in between, the signal is pretty much the same. Your SINAR will not be good. Well, if the cell are not loaded, it's not a problem, but if everybody is connected, then the loads start being high, and then you hit the threshold, you wanna switch. So you are connected on this one, but this one, you're hitting the threshold. You wanna connect to the other one, but the other one also you hit the threshold. So you go back to this one, and then you go back, and then this is what is called the ping pong effect. So this is one of the bad thing about all this mobility management. Yes, it's good. When you're moving, even at high speed, it's good. But when you're standing still in what we call a handover zone, it's not good. This is why a good design will take that in consideration. And usually the handover zone should be on an area where there is nobody sitting or standing. So it's either within the wall or whatever. Like, you need to pay attention to that. That's one of the things.
Well, I think that's good to highlight, you know, some of the different design aspects that you need to start thinking about. It's not that, you know, problems go away, other problems might be introduced that you have to solve for as well.
Yeah, I mean, really awesome points, and I want to mention two things. I mean, one is this ping pong potential issue. Of course, you can put some hysteresis and some thresholds to kind of slow these things down. You can put some time to trigger kind of things. But another aspect is when you get into the enterprise environment, what we found out is these boundary regions are not that many. Because what will typically happen is in an environment like this, you will have a dominant AP covering this. As soon as you go out of the corridor, there will be another one. So these boundaries physically are not that many in a typical enterprise environment with the walls and so forth. You kind of get these compartments of coverage by certain APs. Now, if you have a very open environment, it's a different story. But it goes both ways. Like in a warehouse environment, what we also observed a lot is you may be stationary, but the environment may be moving, right? And these metal objects are moving at very high speed. And at one point, you know, you have an AP which is serving you, but in a few hundred milliseconds, something can come and block you because maybe a forklift or something passing by. Now you have to quickly hand over. Although you're not moving at all, your channel switched on you so fast. So in those kind of situations, it makes a difference to have that ability for fast handover. By the way, handover, roaming, like tomato, so these are like all the different jargons between the two. Yeah.
Anybody else want to chime in? Jennifer?
It occurred to me just a moment ago that I can make an analogy of how we've learned how to do things in Wi-Fi. It's kind of like for the same reason that we have the home row key on the typewriter is the QWERTY home row, is because back in the day the typist typed too fast and would jam up the typewriter, so that's why we have the home row as QWERTY. It used to be Dvorak. Well, the LTE is like the Dvorak, and we can start typing faster and like disband with how we've done things to make use of, you know, typists that type too fast, like you slowed down the forklifts to make the system work. Yeah.
Okay, cool. All right, next topic. Leading right into those design differences or characteristics. So, you know, we have different design targets for signal strength or receive power compared to Wi-Fi versus LTE. That's kind of a, you know, a very visible, dramatic difference that we can talk about. We talked a little bit about coverage ranges already for either voice, data, and capacity, or just basic coverage. We talked a little bit about cell edge performance already, I think, and then channel planning. We do a lot of channel planning in Wi-Fi. Let's talk about some of the differences between channel planning and Wi-Fi and how we might do it in LTE. So who wants to kick this one off?
To start, just those of you who don't know what RSRP is, it's reference signal receive power. Why it's so low compared to Wi-Fi? Because it's the signal level of a resource block basically. So it's not the channel width. So you need, like, for a 20 meg channel, there's 1200 resource blocks. So your total RSSI would be like 30 dB high or something. So this is why it's low power, and also at this level, your noise is basically around neg 120. So you have like at least 15 dB SNR to start with. So just to clarify this.
May I ask you a question that has to do with the practical application that we saw doing the test, doing the lab tests, during the deep dive? Now, with the cell edge performance, allowing clients to stay connected for a longer or whatever you call it, low kilobit data rate, isn't there more of a possibility to experience sticky clients? That's actually something that came up while we were testing in my team.
Emma, do you want to tell them?
I mean, sticky in the sense that we just talked about the fast handover, right? How fast the handover is. So I think if you're on the same channel, if two APs are working on the same channel, and as you move from one to another, as soon as the other, the next AP, the target AP, as they call it in LTE, becomes stronger, the device quickly can hand over. That's very fast. Now, if they're on different channels, now it's interesting, right? Because you can keep going towards the other AP, and you may still be in good coverage from your source AP, and as you get closer to the other AP, it's on a different channel now. So you don't have that, like, because since they're on different channels, your signal to the SINR doesn't change very fast. So you can go all the way close to the other AP, then can do the handover. So it's kind of a different behavior, and that affects the planning aspect. And then you have the intra-frequency handover versus inter-frequency handover. And then the UE needs to monitor the other channels to see which target AP is the best AP at a given point. But this also gives you some flexibility because you have a larger kind of buffer zone, because you can go further and further closer to the other AP. Even if you didn't hand over, you're still good with the serving AP. So that's the key aspect of the design. If, yeah, and then you have a controller, yeah, that can help with the MME and the EPC to control of this. But it's a key design aspect. If you're operating same channel, universal frequency use versus maybe frequency reads of 2 or 4, that affects your handover thresholds and parameters.
Yeah, I think what we hear a lot while you're handing that over is that in Wi-Fi, you know, people would walk and be mobile and they'd stand underneath a Wi-Fi AP and be like, why am I not connected to the APM right under, right? And so you're saying that might be a little bit different behavior that might be expected in LTE if it's because the...
If you don't configure this inter-frequency handover parameters correctly, you need to configure them so that the device is looking at other channels and constantly reporting that to the AP, which goes to the MME, and then there's a decision that's made, okay, now you go to the other channel. That's all in there, but this will configure.
That's what I wanted to explain. Since the handover, or if you call it roaming, is controlled by the infrastructure, there are thresholds set to look for another server or another AP or another eNodeB, call it whatever you want. And if my threshold by default is receive signal level, by default the manufacturer usually it's minimum whatever, neg 107 I think. So if you're not getting to this signal level, the UE or the device will never look to change. It will stick, right? So in the same channel environment, you have the other threshold. As soon as you go away and you are on another coverage area from another server, if it's the same channel, means at a certain point your SINR from the first server will degrade. So you have to switch to another one. But in the scenario of two different channels, you're not getting SINR degradation. Your SINR is still good. Even if your signal level is dropping, basically your SINR is your SNR. There is no interference. In this case, you would need to make this what we call RX-LEV-min, or minimum receive level where you decide to switch. You need to tighten it. You need to, instead of making it neg 107, you make it neg 100 or neg 95 or neg 90. So you define your boundaries of your eNodeB server, and you say, okay, after this point, I'm expecting this signal level. If you get to this area, please look for the other one, even if it's another channel. And then you could define priority. You look for this channel first or this channel first. Well, technically in enterprise environment, you set them at the same priority. But in the cellular world, you could define different priorities. Like this channel is 20 meg, I would prefer this as priority. This is 10 meg, this is second priority. This is 5 megahertz, this is the lowest priority. So check for this one first and this one first. So yes, you end up with kind of sticky client situation, but it is because it was not set up properly.
Okay. Anyone else want to chime in on anything design? Okay. We talked a bit about density and congestion, so we maybe about density handling as far as number of clients that can be connected to a radio. Latency, maybe something that we want to touch on in high density environments. How the protocols each handle latency and what that looks like. Management and control overhead, we haven't really talked about or touched on yet. It kind of increases in Wi-Fi with more SSIDs, or depending on a lot of those nerd knobs we have for data rate controls, or whether or not we have clients associated, or if they're probing a lot. And then different metrics that we use to measure channel quality, like channel utilization in Wi-Fi or RSRQ in LTE. Anyone want to chime in on any of those topics?
Yeah, just to continue on the same subject, you could also instruct the device to look for another server with RSRQ. Means even if your signal is good, your sign-out is good, but the cell is starting being loaded, please check another set that might not be loaded. So RSRQ also is a good one to do a load balancing, basically, without having to meet the threshold of signal and interference.
So I'm an old guy, and I try and relate things to things that I remember. And this is the token ring problem, or the token ring benefit, if you will, which is you have a consistent scheduler in place, or in the instance of token ring, a token that gets passed around, and that becomes the priority on your network. That scheduler becomes the thing that rules all. That's the thing that we broke in Wi-Fi, because you can't do that, because you have to be nice to your neighbors. Token ring networks of the vintage would way outperform Ethernet networks under the same load, because the scheduler, the thing that said, okay, now you can talk, was the thing that was prioritized above all else, right? You take that and you put that control into the hands of a stupid client, and you're going to get stupid inconsistent results. When you put that in the hands of something that knows better than the client, that predictability is worth its weight in gold.
And maybe I'll just make a general comment. I mean, some of these things sound really complicated and hard to configure and so forth. But I mean, this technology has been out there for quite some time, and many of the issues that we're kind of highlighting here are solved and has been in use for more than a decade. Now, enterprise is a different twist in all of these use cases, but they're all the knobs, and it's kind of clear in terms of how to tune these knobs to change certain behavior and how to add quality of service and so forth. So just wanted to highlight that as well.
Yeah, perfect. Anybody else?
So I think one of the things that's really interesting that I did not realize was that management and control is dedicated to tones, correct? So in Wi-Fi, we know that all of our management traffic takes up, every 2.4 milliseconds, there's going to be a beacon, per SSID, right? So it takes up time, right? In this case, instead, it's taking up tones, it's taking up frequencies. So there isn't that constant stop and start of the network waiting for that. And I think that was one of those aha moments that somehow I had missed. I mean, even understanding the whole separation of both frequency and time, that was one of those things I missed. And when that aha moment came to me, that was definitely like I get this I get this. And again, it goes back to that efficiency that we don't even come close to in Wi-Fi.
Just maybe to add on to that, I mean, the other aspect is now all the devices know when their control signals are, so they can just wake up, check if there's any page for them, just very short amount of time. If there's nothing, they can go back to sleep. And you kind of distribute this, as you said, like you're not dedicating a certain time slot, you're just spreading it across time slots, across tones. So every time slot you're serving many users, but sending some small amount of control information from the AP. And I think that has both benefits in terms of quality of service is not degraded, because you still use 90 whatever +% of the resources all the time. And also the devices can wake up in their corresponding time slots for a quick time period, and that has some battery life impacts and so forth.
Awesome. Okay, maybe to wrap up the conversation, I'll just have each of you maybe give what you're excited about with the evolution of these technologies moving forward. So in Wi-Fi, obviously we have Wi-Fi 6 with 802.11ax come out, offering to better capacity and spectral efficiency, and we'll have more spectral capacity with 6 gigahertz. And on the cellular side, we're moving toward 5G that offers potentially much higher bandwidth than has been capable of before, more flexibility for uplink versus downlink traffic and things like that. So maybe we'll just go down the line and, you know, what are you excited for coming out in either technology, and what are you looking forward to?
I mean, I start with why are we even talking about CBRS? As Wi-Fi people, it's not uncommon to find a whole ton of Wi-Fi people who don't deal with outdoor bridge links, point-to-point bridge links, license frequency, anything. They just do straight up carpeted office indoor. And why on earth are we sitting here at a conference that's generally talking about Wi-Fi technologies, talking about this thing that's CBRS? Why in the heck is it even really important to us? And the answer in my mind is it comes back to the clients. We as Wi-Fi people see generational adoption of clients, and we see this slow roll, and then we see the uptick, you know, far into the right. We're seeing it with Wi-Fi 6. We saw it with 802.11ac. We saw it with 802.11n. It just so happens that most of our Wi-Fi 6 clients, generally speaking, also have this fantastic other third radio in them, and they're going to be in your enterprise spaces. They're going to be in your carpeted office spaces, and them being in your spaces is a fantastic opportunity for us as Wi-Fi people to say, how can I start meeting other business demands that I couldn't do on the Wi-Fi space? We have this huge inbound wave of devices that are going to crush us, and many of us don't even consider the new devices that are rolling off the lines are going to be CBRS enabled. So yeah, it's not going to be next month, but you need to be looking beyond next month to what's next year going to bring, what's the next 2, 3, 5 years going to bring. And if you're not at the front of that, you're going to get steamrolled by it.
And to add to that, it's amazing how complementary those two technologies are. And we've been saying for a long time that 802.11ax or 5G LTE, yes. The answer is not one of or the other, it's yes. And I strongly believe that after the deep dive that we had the chance to attend, that for the Wi-Fi professional, this is a complementary technology. It's going to push our understanding of Wi-Fi and wireless in general further, and maybe even make it better. So that's awesome. And the only thing that we didn't touch on so far, and you know what's coming, right? I'm gonna tell you, CBRS in Canada. So I can't wait to see what's available in other countries, because you guys in the U.S. are very lucky to have that much spectrum for CBRS, and you get to experience the benefits first. So.
Yeah, unfortunately, but I think there's some things happening already. Some documents for comment is already published. I can share some of that with you. I think the regulator in Canada is looking at this very seriously, but it may take a few years. I don't know, unfortunately.
So you get to solve all the bugs, and then you're
exactly. Yeah, that's one way to look at it. So really, I mean, we talked a lot about some of the benefits of LTE, and that will get even more, right, even higher benefits with 5G. But if you look at this graph, I think this is kind of informative. I mean, they're all going in the same direction, right? I think that's kind of exciting. Like all these things that we are talking about, OFDMA and other things, are slowly finding its way to Wi-Fi. And in my mind, to be honest, I think LTE and 5G has a lot to learn from Wi-Fi as well. And especially when you bring this technology to an enterprise kind of environment, there are a lot of great things that the Wi-Fi ecosystem has done over the years. And the real exciting part is how do you take this great technology with maybe Phi, Mac layer capabilities and fit it to the right enterprise architecture so that all these great applications, great things that we are excited about really happen, right? And that's the part that excites me the most. So.
And your solution makes it fairly easy, and yeah, easy is the best word that comes to mind, to abort. Janelle, abordable, affordable for the wireless professional to get involved in the technology too.
Yeah, I think that's the really exciting part. I think you're right on it. And how do you bring that technology in a consumable way, in a frictionless way to an enterprise environment? I think that's the exciting part.
Really, when I think about CBRS, what I think about is we know everyone in our enterprise organizations is carrying a device. And these have many uses beyond just simply checking email and Reddit and whatever else, right? These get used in hospitals, and in fact, I'm aware of a hospital where they buy iPhones and they never put them on cellular service because they have to be able to control that data that comes to and from that device, right? So they have hundreds, if not thousands, of iPhones that never hit a cellular tower because there's a policy problem there. With CBRS, we address that policy problem. We now have full control of that data path. We now have the full control and full ability to apply policy, whether it's security or access control or whatever, to those devices in a way that we've never had before. And then when you tack that into what you actually brought up earlier, which was one of the big notes I made, which is not only can I do that per device, but I can do that per application per device, right? Where maybe there's a support application that needs just raw access to the internet, and then there's an internal application that needs very, very, controlled access to a single server. That's some capabilities that we've never had before. For this type of device. That's what I get excited about. More than anything else, it's that right there.
And what I find exciting is that we're going to, as Wi-Fi engineers, we're going to suddenly have access to control and order and reign over all the client devices, which we've never had before, without us having to make a giant leap into becoming part of the carrier. But the infrastructure, like we still get to be Wi-Fi engineers, but we're suddenly getting a toolbox that we've never had access to because we've never been part of the carrier solution.
Three things. I'm really excited about the coming of Wi-Fi 6. It kind of brings a lot of hope that Wi-Fi in public venue will not suck anymore. So I'm excited that it's kind of going into the efficiency that LTE has. Hopefully, we're going to see that soon enough. 5G, I hear a lot of comment that why do we need it, especially like why do we need that much spectrum? Believe me, if you haven't worked for a carrier, for a wireless operator, you don't know what you're talking about. It's a struggle, like as a designer to design a network with like just 5 or 6 channels, especially if you're doing like a stadium or something, it's a struggle. You don't have enough capacity. Like millimeter wave, what's bringing is more capacity. And there was no more channel to be used in North America. It's just all operator used whatever channel they had, and they had to reuse it. And it was really, really difficult. So it's exciting for people who are doing network design in the cellular world that 5G is bringing more spectrum. Now, what I'm more excited about is really CBRS. Why? It's kind of having the possibility to solve some business challenge and some industrial need that Wi-Fi was not able to fix. And then you could use LTE without having to rely on a carrier. The carrier, they have a lot on their plate already, right? So being able to do that internally or at an enterprise level and solve some challenges and meet the needs that Wi-Fi was not able to do. So you can complement that with another technology that it's open, kind of. It's really exciting. That's all I have.
Great. Well, I want to thank all of the panelists for joining us and providing your opinions and perspectives on these technologies. And I want to thank everybody out there for watching on the video feed as well as live in the room here. I appreciate it. And thank you. And don't forget, we have the Salona community spinning up in the next couple of weeks. So if you're looking to learn more about CBRS or private LTE and 5G, we're looking to grow that community for open discussion and training content for everyone. So hopefully we can bring that to you and we can have good participation as well, and we'd love to have you. So thank you and have a good evening, everybody.